Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're going to talk about 2-1 Atomic Structure of the IB Chem SL curriculum. Thank you to Bass Pro Shops and Costas for sponsoring this episode. Costas, born on the water. Let's go ahead and get started. So the atom, all things are made of atoms. So this particle physicist here, Richard Feynman, said that if we were to lose all scientific knowledge, but we're only able to retain to one statement, it would be that all things are made of atoms. Because with this statement, we can compound on this idea to come up with a lot of the scientific knowledge that we have today. So a very important statement. Now, the model of the atom has changed over the history of science. So back in the 400 BC, Democritus was able to figure out that atoms were the fundamental particle of things. You could cut things into tiny, tiny pieces. Eventually, you would get into the atom, which meant indivisible. It wasn't until 1897, many years later, that J.J. Thomson did his experiment on the electron with the cathode ray tube experiment, and he was able to come up with this plum pudding model. Uh, Thomson's plum pudding model, he was British, and so this is a British dish, but had the negative and the positive charges of the atom kind of spread throughout the atom. In 1909, Rutherford, with his gold foil experiment, shot alpha particles at a gold foil. Noticed that most of them passed through, but a very small percentage was reflected in a different direction. So he found out that the positive charges were all localized in this very small area called the nucleus, while the electrons he thought, were still distributed throughout, like the plum pudding model. Bohr's model in 1913 found that the electrons aren't just randomly distributed, they actually are contained within these orbitals or shells. And each of the shells actually have very distinct energy levels about them. And taking on Rutherford's model that the protons, and then they discovered the neutron, the protons and the neutrons, through the neutron was discovered by Chadwick, are found in the nucleus. In today's model, we have the charged cloud model. Pretty much we said that we cannot determine the location of these electrons, and so we have a probability of where the electrons might be, and we'll talk about that more in section 2. So let's talk about our three fundamental particles here. We've got the proton, the neutron, the electron. We can see that the proton and the neutron, in terms of mass measured in kilograms, weigh about the same. And the electron, it weighs a lot less than the proton and the neutron. If we look, we pretty much consider the electron's mass to be insignificant when compared to the proton and neutron. So we're going to normalize this by saying the proton and the neutron have about 1 AMU, atomic mass unit of charge, or sorry, of mass, while the electron has pretty much almost 0 AMU. It's not 0, but it's very close to 0 because it's such a small number. The charge, we can see we've got about 1.6 times 10 to the 19th coulombs. The proton has 1.6 positive coulombs, and the electron's negative 1.6 coulombs. The neutron does not have a charge, so it's at 0 coulombs. And so we will see this represented a lot in this class, where the element symbol will be written with a bunch of numbers around it. A will represent the mass, which is the protons plus the neutrons. Z is going to be the atomic number, which is the number of protons. And then the charge, sometimes written in the upper right, is going to be based on the number of protons and electrons, with the protons giving us, remember, +1, and the protons giving us +1, the electrons giving us -1. Sometimes A and Z will be switched, so the atomic number will be on top. Just know that A will always be the larger number. Isotopes. Isotopes are atoms of the same element with the same atomic number, but they have different mass numbers, meaning they have different neutrons. So here's carbon. Carbon will always have 6 protons no matter what, because if it had 7 protons, it would be nitrogen. If it had 5 protons, it would be boron. So it'd always be 6 protons. But they can differ in the number of neutrons that they have. So we have carbon 12, which has 6 protons, 6 neutrons, 12 representing the mass. We have carbon 13, which has 6 protons and 1 more neutron, so 7 neutrons. We have carbon 14, which is 6 protons and 8 neutrons. Isotopes all are going to have very similar chemical properties. It's because chemical properties are determined by the number of electrons. And you can see here that they all have the same number of electrons. But they're going to differ in their, oh, that's supposed to be physical properties. They're going to have different physical properties, such as mass. If they have a lower mass, they're going to have faster rates of diffusion, lower densities, and lower melting and boiling points. Ions, these are atoms with equal number of protons and electrons are going to be neutral, but if you gain or lose electrons, then you're going to form an ion. If you lose electrons, you're going to form a positive ion called a cation, and if you're going to gain electrons, then you're going to become more negative and you're going to be called an anion. The way I remember this is, so cations are positive, so I just remember that cats are positive, you know, like the paws of a cat. Cats are positive. So, or that cation has a T, and the T kind of looks like a plus sign. So two ways to remember it. Either a cation has a T, which is positive, or cats are positive. Okay, relative atomic mass. So if you take a look at the periodic table, the masses that are shown there are not clean numbers. Like if we were to just add up, like let's say carbon, has 6 protons, 6 neutrons, the mass should be 12. But if we look at the periodic table, the mass says 12.01. Why is that? Well, it turns out that the masses on the periodic table are averages of all of the isotopes. So it's an average of all the carbon 12 isotopes, the carbon 13 isotopes, and the carbon 14 isotopes. That's why the mass is 12.01, because it's an average of all those three. So we're going to see some problems that have to do with these. In order to do this, we're going to assume a couple of things. Number one, we're going to assume there's 100 particles. That's going to help us out with the calculations. If they only gave us one, then we'd have to subtract from 100 to figure out the second abundance. And the formula below is shown, and we're going to be using that formula to figure out the atomic masses of various elements. So let's take a look at an example. Here we have a mass spec data, which we'll talk about more in a sec. And it shows us the relative abundance of two isotopes of gallium. One isotope of gallium has a mass of 69, and one has a mass of 71. Now, the one with 69 has an abundance of 60%, while the other one is 40%. So we're going to assume we have 100 atoms, and if we do that, then if you had 100 atoms, 60% of 100 is 60, and 40% of 100 is 40. And we're just going to multiply that by the masses. So and we get 6,980. And then we're going to divide by the number of atoms, so we get that the atomic mass of gallium should be 69.8. Here's a mass spectrometer, and the way it works is you put a sample in here, and it vaporizes it into a gas, and we're going to accelerate. And based on the mass, we're gonna have a magnet here, and the different masses of the isotopes should be deflected different amounts. And based on the deflection, we can calculate what the original mass of the substance was based on how much it gets deflected, and we can measure that deflection on this detector here.